Swayam Prabha. Digital India. Educated India.
We were looking at, or we started looking at vertical dynamics, and that's what we are going to do for the next 5-6 classes. And we already noted that there are two important things in vertical dynamics, two important things that we have to look at in vertical dynamics. One is what we call as right comfort, okay, and the other is what is called as road holding. Okay, so right comfort and road holding are the two important things that we are going to see in this part of the lectures. Now, of course, road holding for a common car may not be an issue, maybe more for formula cars, racing cars. This becomes very important because of certain differences between the usual car that you drive and that of a car which is driven for, say, Formula 1 racing. Okay. So, what is more important for, of these two, what is more important for us is what is called as this right comfort. As we had done earlier in this course, where we had looked at a bicycle model and looked at handling from a very simple model in order to understand the concepts. And then we, of course, we did some modifications to these models. We looked at the assumptions that we had made and then slowly removed that assumptions and then brought out a complete picture. Like that, we are going to look at this right comfort, okay, from a very similar perspective, and we are going to first put down a very simple model and then draw some conclusions. The point is this, that there are a lot of assumptions in the simple models. Is it that it's not valid? One of the first things you have to notice is that when you have a very complex model that you may put up in one of the commercially available softwares, like Carson, Adams and so on, they need to first have a model in order that we put it inside these softwares. So a first cut, first analysis is always good to do that, to do before we go to bigger models, and that's why these models are important. Let's go straight away to this model. There are a number of names to these models. We will know as we go along what are the names to these models. We will look at what is called as a half car and a quarter car model. This is a very standard technique. You would have noticed that in your control system course, where we will going to replace the system with spring mass damper, and maybe even in your vibration course. Okay. So that is our simple model. You would notice that the tires have been replaced with springs, which I would call as the the spring stiffness K front tire, K rear tires. Okay. Notice that we have not put a damper to the tire, okay, though it looks very attractive, but usually the damping effects are neglected, not very high, and it's neglected. Okay. And this is what is called as our unsprung mass. Okay. So we will call by small m, okay, unsprung mass in the front and m unsprung mass in the rear. These are the stiffnesses and the damping characteristics of the suspension system. So we'll call that as KSF, CSF, KS rear, CS rear. Okay, that is the sprung mass, and we'll call that as M sprung mass. okay, and that we also include a j theta. Notice that we are going to have theta, which is pitch, can be considered as one of the degrees of freedom. So we are also putting j theta in our analysis, so that theta can be considered as in the analysis, and we'll follow the same thing as we had done before. That is this distance a, and that is the distance b from the front and the rear. The input to this is obviously the road input. Okay, so we will call that as, say, road in the front and road at the rear. We assume here in this model, note this model, what we have done is, like we did compressing the bicycle model and so on, what we have done is to compress that and put it like this. Okay, so in other words, we are designing half the car. People call this sometimes as half car model, because the other half is compressed and put into one thing. So what is possible to have here is the pitch mode. We are not considering roll. In other words, what we consider in this model, or the assumptions that we make in the model, is that the right input, the right side of the tire input is the same as that of the left side of the tire. Okay, both the inputs are the same, or in other words, the road is such that right and left side are the same here as well as here. Right? Okay. So of course, this is a question of time. Okay, that is the input into the model, and we assume that there are displacements. Let us call this as y1 and y2. Okay, and let's just put the displacements here as z1 and z2, which can be expressed, of course, in terms of the what I'll call as z or zs. Okay, in India, we have a tendency to call z as z. Okay. So you know why? We're used to calling this as z, because z is never used as z. If you got zebra, z. Okay, so if you notice that z is always used as z, so the reason why usually people don't call this as z, but they call it as z. We are used to calling this as z. When I say z, there are problems for some of you to follow what I mean. So anyway, so that is the z1 and z2. Okay. So now what am I going to do? Very simple, nothing great. I'm going to write down all the governing equations, equilibrium equations, okay, which are going to be a second order differential equation. That's all I'm going to do. Okay. In fact, you can write it down. There's no issue. What we are going to do, of course, I can write this in terms of s and theta, okay, or in other words, it's possible to relate both by means of this relationship. Okay, or I can write it in terms of zs and theta, or in terms of z1 and z2. Okay, right? Fine. Now let me write down the equations, the governing equations, and you will understand what are the degrees of freedom. Okay, so the first is, so I said that if I want, I can change it. That's all I want to know. I want to state. Okay, fine. Now let's consider each of these masses separately, right, and write down the governing equations to it. Okay, and then of course these are the road inputs. I just want to give you a small background to this road input. Okay, there's a tendency for people to just measure the road profile. Okay, just measure the road profile. Road profile measurement projects which I think a couple of students have done before you, maybe 3-4 years ago. So road profile measurements are done using laser sensors, and so on. And there's a tendency to just input that straight away into this model. Is that correct? Is that right? No. Why it's not correct?
You can change later.
No, that's correct. But I'm saying a particular road where you're doing measurements, okay? I measure this. I can do that using,
Speed also matters.
yeah, okay, that's very good. We're going to consider the speed.
Tire may damp some of the.
Correct. Tire acts as a filter. Okay. Now, because tire, that is what is called envelopment characteristics of the tire. So the tire, as it goes, okay, is not going to be like this, but it's going to be like this. Okay. And it is not, in other words, it is not the true representation of the road. What the car sees is not the true representation of the road. So when I put this RF and RR, they are not road inputs, which is usually called in many textbooks. It's not that just the road profile, but it is the profile which the car sees after this high frequency filter called tire, which filters off not due to its stiffness characteristics. We're not talking about that. That I have already put it here, but more due to the envelopment characteristics, so that the what goes inside is what is felt. If you go and sit in this tire here, this region, what is it that you feel is what we call by RF and RR.
Do we really know what that is?
Yes. So there are models, you're correct, there are models to understand and put that as an input. Okay, this is a very important problem, been tackled well in the tire models. Okay, envelopment characteristics, as it's called. If you go and look at Swift model, okay, then you will see that there is an envelopment characteristics as a part of the model, but that is very important. So whatever model you put in, it's very important that envelopment, you understand what is envelopment. Envelopes, okay, that's what goes as an input. That becomes very important. Let's now straight away write down these equations. Now, so ms into, I would use that, is equal to f front plus f rear, which I have to be consistent. That's why I have to refer to that notes, because I don't want to change my thing. So let me call that as f1 and f2. Okay. I have a tendency to change this. I want to be careful if you don't understand anything. Okay. So let's call that as f1 and f2. So f1 and f2 are the inputs from the front and the rear, respectively. So what's the second equation? J theta, moment equation. J theta into theta double dot is equal to moments f1 into A minus f2 into B. Okay. So the next equations, two equations I'm going to write for the unsprung mass, the front and the rear. Okay. So m unsprung mass, the front y1 double dot is equal to, so write down the force balance equations. Okay, MUF, right? So MUF into y1 double dot MA. Write down the force terms. K front tire multiplied by, now that's a spring, so all of them are RF, so RF minus Y1, all of them are function of time, so I'm just removing this T, plus K suspension in the front. So there are two things here, so Y1 and the other side is Z1. Okay, so Z1 is written in terms of course, I already written that. Plus right? So similarly, I can write down m u r into y2 double dot is equal to krt into rr minus yn plus ksf into z2 minus y2. I'm not going to write down or derive every step because this is algebra. I said that, I told you already that you have to work out some of the steps that you have. Yeah. Oh, sorry. Right? Oh, okay. What's happening to me? Okay. So good. Let me sheepishly say that I just put it so that I want to know whether all of you are awake. Okay. So all of you are listening and you're understanding. That's very good. Okay. What's F1 now? Write down F1 minus K Fs into Z1 minus Y1 minus CFS into Z1 dot minus Y1 dot, okay, and F2 is equal to minus K rear spring into Z2 minus Y2 minus C rear spring. Okay. Right. Then what else have you written? That's right. Okay. Now, as I said, I'm not going to do the rearrangement every step. Obviously, I'm going to write this down into this. By the way, what are the degrees of freedom? What are the degrees of freedom? How many degrees of freedom are there? 4. What are they? Y1, Y2, Z1, Z2, or Y1, Y2, ZS theta. Okay? So there are 4. So this is basically a 4 degree of freedom model. Okay? Let me prompt what I'm going to do. The first thing I'm going to do is to cut this and make it into what is called as a quarter car model. Okay? I'm going to compress that and put that as 1 quarter car model. Okay? In fact, more interestingly, what I'm going to do is to cut this and consider the masses to be distributed to the front and the rear in the same ratio as we had done before, and then consider this as 2 quarter car models, 1 to the front and 1 to the rear. Okay. So what I'm essentially going to do is to rearrange this. Sorry. Okay. Rearrange it. I'm going to write down the results. Of course, U is equal to and R, which is the load, of course, M is quite straightforward. Okay, so that's quite straightforward. You can see all the what am I doing? I'm very simple, 4 equations. I'm just rewriting it in a matrix form. Okay, you know why I'm doing it. It's quite straightforward. So the next is the C matrix. Rearrangement gives us note that I'm going to replace Z1, Z2 and all that. So rearrangement gives me something like this: CFS plus CR, yes, CFS, A minus CRS B minus CFS minus CRS. Okay. Okay. One of the things which I had pushed in without elaborating is that the spring stiffness is a constant. In other words, I had pushed, when I wrote down this equation, I had pushed that the spring is a linear spring, which is definitely not the case with most of the suspension system. It's a hardening spring. Okay, so the suspension spring is not going to be a linear spring, but as I told you, we want to get the first cut results, what we call as first cut results. The reason why we have made these assumptions, and that this is, the damping is characterized by a simple number, and the spring stiffness is characterized by a simple number, right? And the K matrix, we will write down the K matrix. Here the results are very interesting. Unfortunately, we can't jump to the results, so we have to you would see, notice that it's very similar to C matrix. Because there is no C there for the tire, that's missing the stiffness of the front tire and the rear tire. Okay. We can solve this, not a big issue. Okay. You have MATLAB. Okay. You know, if I give you the functions, okay, you can solve it. But I'm not going to do that. Okay. As I said, we want immediate some results. So this is a complete half car model. Okay. In fact, just for the fun of it, write down equations for a full car model. Okay, write down equation for full car model, and it's possible to solve. It's not very difficult. You can solve that as well. But nevertheless, you write it down just to get a feel of how we're going to deal with it. In other words, if you go to a full car model, then you have a pitch, then you have a roll, right, the other direction, and then, so for the body, you have the Z, and then pitch and the roll, right? You can write it down. Now what I'm going to do is to split this to get some very interesting results. I'm going to split this into two models or two quarter card models. Later, I'm going to consider a similar version of our half car model in order to understand, okay, more about this model. So the first thing is that this is what most of the companies do, okay, as a first cut. Why do they do it? Immediately, if you want to look at suspension tuning, if I want to look at optimized suspension, okay, then it becomes very simple to understand this, right? And so we use this for optimization of the suspension system. So the first thing I'm going to do is to look at what is called as the quarter car model. As I told you before, I'm going to redistribute the mass, right, and put that front mass is equal to, how do I put that? B by L into this sprung mass, and is equal to A by L into the sprung mass. Okay, so now the equations are the same, front and the rear. So I'm going to consider only one of them and put that M as a small ms, and write down the equations. Okay, so how does this look like? As I said, I'm going to cut it here. So the front and the rear will have the same or similar or same equations. The only thing is you have to replace corresponding with the ms, k front, k rear, and so on, right? So we will write down one common thing. So that is our sprung mass, and then that is our suspension, that is our unsprung mass, that is my tire, and the tire is on the road. So that's my what is called as quarter car model. Quarter car. Okay. So let me write down that. Is equal to, as I told you, this one we would call that as Z, and that is Y. Minus C into Z dot minus Y dot. I want you to check this. Is that correct? Of course, that's Ks, that is C, and that is Kt. Is it positive? Is it correct or not? I know because a few questions, last one of the earlier courses that people had confused between. See, it's very easy when I put a force. So when I have two things which are moving, okay? So what happens when Z is more than Y? That, in other words, this is positive. Okay, what would happen? Let's just look at the spring. Z is more than Y. So what will happen? Pull down. Okay, so the force will be in the negative direction. So, but my m s z double dot is in the positive direction, so I have to put a negative there. Right? Now I know your question. Solved? Any other question? Okay. If you want, write it like this. If you want, write it as ms is equal to force from the spring plus force from the damper. Okay, and then write down. Right? Fine. And so this is again, note that we are looking at 2 degrees of freedom, z and y. Of course, r is the road input. Note that all of them are questions, are functions of time. Okay. Now, I have to have a strategy to look at it. Why am I looking at this? One, I said that I want to optimize the suspension. Okay. So, in other words, you can look at this simply from point of view of natural frequency, determine the natural frequency, okay, and we will see we can optimize the suspension and so on. Right? In fact, just want to state even before we go there, so you will get, okay, in simple terms, in terms of what you have studied, you would see that there are 2 natural frequencies. Okay, one is called as the wheel hop frequency, and the other is the body frequency. Right. But more important thing also is that I'm going to write down the behavior or the ratio of the y in terms of y to r and z to r. Okay, I'm going to write that down. Now, I'm going to assume that this r is a complex exponential function, which I would write that as r e power I, say, omega t. Okay, as a complex exponential function. This is, you would have studied this already in controls. Okay, so what is this system? This is what is called as the linear time invariant system. Linear time invariant system, nothing is going to change. Okay, and that if your output is delayed, input is delayed, output is also correspondingly delayed, and so on. The beauty of the system is that if I now give a complex exponential function like r e power I omega t, the output is also a complex exponential with the same frequency but with a phase lag or phase difference, with a phase rather, right. So, let us call that as, say for example, this thing, let us call that as y e power I omega t plus phi, okay, which I would combine them together and write that as y e power I omega t. So, the y is actually a complex function, takes into account the phase as well, right. Now, why am I doing this, or what is the use of this, or how do I use this property called linear time invariant function, that the complex exponential becomes this is used, how do we use it, or why do we put it like this? Basically because whatever be the input can be split into, in the time domain, you can split it into complex exponentials or sum them up as complex exponentials. Okay, you had seen this for example, in Fourier series, right, where you had a periodic function. The periodic function was expressed in terms of sine and cos, which are okay, which can be expressed also in terms of complex exponentials. Okay, that is for a periodic function. You can also express, say for example, the road input as in terms of complex exponential, in terms of a number of frequencies, using another technique, okay, which is very well used, called Fourier transforms. Okay, and the way we are going to calculate that is what we are going to call that as fast Fourier transforms. Okay, so a Fourier transform converts whatever be the input into a number of complex exponentials, and hence if I now get a solution for one complex exponential, okay, and using this time superposition principle, it is possible for me to get the output for a number of such complex exponentials. So that's why I'm interested in that complex exponential where y is also a complex function, and so I write it like this. All right. With that background, let me write down. I'm going to, as I said, quickly run through because we're running out of time. There are a lot of things to cover. Okay, so input and output are of the same form. Substituted, what do? Put that in the governing equation. I'm going to get omega squared here and so on. You do that. I'm going to express this final form. You know, the two equations. Do that. Of course, R is real. So from which I'm solving this and writing down Z by R and Y by R. Okay. And so that is Z by R. The same thing as denominator. Let me write that down as something like this: d plus IC omega E, where d is equal to, expanding that, though this looks formidable, there is nothing that is difficult in this. Because of the number of terms, it looks very complex. Okay, so we're going to, as is usually the case, I'm going to simplify it later. Minus okay. So of course, if you want a solution, look at that. Everything is known. It's straightforward. There's nothing very difficult, right? Notice also that both y and z are complex. Okay, we'll do the interpretation in the next class. Okay, but let us first understand what it is. So in other words, the very first thing is that given an input, the road input as a complex exponential, I can find out what would be the displacement at the unsprung mass position. What's that? So let me call that as G, let's say GZ. Let's call this as GY. You know why I'm calling that as GZ and GY. Okay. So y is given as R multiplied by GY multiplied by E of I omega t, right? Same fashion you can write down Z. Okay. How do I, suppose I give you this and I want you to do a test. How would you do? Practically, I want you to measure this. Before we go further, so this is too much of maths, too much of equations. Okay, tell me, what are you trying to do? What is that ultimately I'm interested in? Okay, right? That's the first question. I'm giving you a car, and I want you to measure. First thing is, I don't even know, you talked about road envelopment characteristics. I don't even know how I get this road envelopment characteristics and so on. Okay, so give me a car. Let me first do some experiments to understand what's happening. First question. So what are those things that you have as an equipment, as a sensor, in order to do an experiment? You have an accelerometer, right? Okay, very good. All of you have used accelerometers. So the first thing you would do is, yes, I have an accelerometer, a data acquisition system, right? So what do? I put an accelerometer here, and I put an accelerometer here, and then start recording the acceleration levels. So now acceleration levels are obviously, can be determined this by this. Y dot is equal to I R Gy I omega t e power I omega t, and I square, that is, in other words, from here it is minus of this quantity minus of that quantity. Right. So once you measure this, suppose I want to know how much of road input has gone in. I have measured it. In other words, I know what this quantity is, right? For let's say that I do FFT, I do all those things. Let's take one frequency. I know what has gone in here. So I can easily find out what is because I know I measured it, I know the other quantities, I can find out what is my actually R. So this is for a particular tire, okay, that is a constant, and so I can use that for any other vehicle. I can use R into e power I omega t as an input for the road, right? So the first thing is that from here, I am interested to determine the acceleration, right? And I'm going to look at how my tire is filtering, right? And also more importantly, how my suspension is filtering all that input, right? Why am I interested in acceleration? Because you would later see that acceleration is the deciding factor for ride comfort. You would see that it is at the tolerance level for a human being would be expressed in terms of accelerations. Okay? So that you can do it by measurement, as well as you can do it by a quarter car model. We're going to give a small twist to this. Is it exactly acceleration? Is it something else? We'll come to that. We'll give a small twist to it. But nevertheless, from here, what we are interested in is the acceleration, right? If you want the magnitudes of Z and R, we will finish this class with that. Magnitudes of Z and R. Of course, you know how to get the magnitude, get the real and imaginary root of real plus imaginary. So that's the two vertical magnitudes. The magnitude of acceleration for these two are given by omega squared multiplied by this, omega squared multiplied by that would give you the two magnitude of acceleration levels. Clear? Any questions here?
How is it going to help? Anyway, this parameters will be different for different speed, and it will also.
Wait. You are right. You are absolutely right. You know, the problem in this is that I have to derive it. I have to show you the equation and then come to interpretation. I know, slightly impatient to why are you doing this, right? That's why I immediately jumped and talked about acceleration. You are absolutely right that this is what we are talking about. A road profile is a spatial or in time domain. Okay, it's sorry, not spatial, but is in the time domain. Is in the as a matter of distance, spatial domain. Right? It is a matter of distance, actual profile. Right? When I put this as an input, I am converting the spatial domain into time domain. So what is that linking factor? Speed. So what is that you get? You know, we'll with the last statement we'll finish this class. Okay. So what is that you get? You see that if I go in the same road, very important point you brought out. If you say go in the same road at different speeds, I am not going to get obviously the same output. Very simple. You see that every day, right? At particular speeds, you would see that suddenly your car starts jumping, and after some time it will come down. Okay. So when is it going to jump? That's an important question. Okay. That's what we are going to see. Right? So in other words, for the same road, speeds give you different inputs with respect to time. Absolutely correct. How is it? We'll see that in the next class. Does that answer your question? Come again. So the speeds are important. I have not yet tied this up. Okay? Speeds are important because speeds, how? Put that down. You know the velocity in terms of meters per second. You know the spatial distribution in terms of distances as meters. Connect them together, and we'll see that in the next class.